This is a video explaining how to differentiate integrals and the fundamental theorem of calculus. An indefinite integral is the inverse of a derivative. So if you differentiate an indefinite integral, it will give you the original function of the integrand. An indefinite integral gives you a family of antiderivative functions with the constant c added to the end, because taking a derivative of a constant will give you 0, and will result in the original function of the integrand no matter what the constant is. Indefinite integrals are solved by doing the inverse operations of what you would do when you differentiate. For example, to take the indefinite integral of x squared, instead of doing the power rule where you multiply by the exponent and subtract 1 from the exponent, you would instead add 1 to the exponent and divide by the new exponent, which is 3, resulting in the equation x cubed over 3 plus the constant c. The fundamental theorem of calculus part 2 states that the definite integral of f of x is the difference between the antiderivative of f of b, where b is the upper bound, and the antiderivative of f of a, where a is the lower bound. This then gives us the area under a curve from the interval a to b. The constants from the antiderivatives will cancel out, so it is not explicitly stated in the fundamental theorem of calculus. If we look at the graph of the quadratic function x squared, if the blue area represents the area under the curve from 0 to 4, and the red area represents the area under the curve from 0 to 2, subtracting the red area from the blue area would give us the area under the curve from 2 to 4, or in other words, the integral from 2 to 4 of x squared with respect to x. Differentiating a definite integral with the lower bound of a constant a and an upper bound of a function of x is explained by the fundamental theorem of calculus, part 1. The fundamental theorem of calculus, part 1, states that if a function f is continuous on the closed interval a to b, then the function g, defined by the equation g of x is equal to the integral of f of t from a to x, where x is between a and b, then that function of g is continuous on the interval a to b, and also differentiable on the open interval a to b. But most importantly, g prime of x would equal f of x. What the fundamental theorem of calculus, part 1, is essentially saying is that if you have an integral of f of t with the lower bound of a constant and an upper bound of x, solving that integral will give you an antiderivative of the function f. And therefore, if you differentiate that integral, it will give you the original function f of x that you integrated. The function is f of t and not f of x in the integral because x is already used as the upper bound variable, so t is used as a dummy variable to replace x. For example, if you have the integral from a to x of t squared with respect to t, the antiderivative of t squared is t cubed over 3, which we integrate from a to x. Using the fundamental theorem of calculus, part 2, we plug in the upper bound and lower bound into the antiderivative function, resulting in x cubed over 3 minus a cubed over 3. Differentiating this will give x squared minus 0, since a is a constant, and x squared is equal to the original function of f of x. The proof of the fundamental theorem of calculus, part 1, is as such. If g of x is the integral from a to x of f of t, then g of x plus h minus g of x is equal to the integral from a to x plus h of f of t minus the integral from a to x of f of t with respect to t. This makes sense as we are taking the area under the curve up to x plus h and subtracting the area up to x, starting from the lower bound of a. If a function is continuous, an integral can be separated into two integrals with an intermediate bound between the upper and lower bound. The integral from a to x plus h of f of t is separated into one integral from a to x and another integral from x to x plus h. The integral from a to x is cancelled out and leaves the integral from x to x plus h of f of t with respect to t. Since g of x plus h minus g of x is equal to the integral from x to x plus h of f of t, we can divide h on both sides to get the following equation. The left side of the equation is in the form for average rate of change, and since the function g of x represents the area under the curve of f of x, the average rate of change of g of x from x to x plus h represents the average value of f of x over the closed interval x to x plus h. Since f is continuous on the closed interval x to x plus h, we can use the extreme value theorem to determine that there is an absolute minimum and an absolute maximum value on that interval. If f of u equals m represents the absolute minimum value, and f of v equals capital M represents the absolute maximum value, we can create the inequality where the integral from x to x plus h of f of t with respect to t is in between the absolute minimum multiplied by h, which is the delta x, and the absolute maximum value multiplied by h. Multiplying by h gives the area under the rectangle created by multiplying the absolute extrema value by the width of h, while the integral represents the area under the curve of the function f from x to x plus h. We can substitute the lowercase m and the uppercase m with f of u and f of v respectively, and we can divide by h to simplify the inequality further. With this inequality, we know that the statement previously that 1 over h multiplied by the integral from x to x plus h of f of t is equal to the average rate of change from g of x to g of x plus h. If we set the limits where h approaches 0, then the value of u and v will both approach x, as the change in x, represented by h, is approaching 0. These limits give us f of x for both the limit for the absolute minimum and the absolute maximum value. Using the squeeze theorem, we know that since both ends of the inequality are approaching the same value, the limit of g of x plus h minus g of x all over h as h approaches 0, which is the form for derivatives, is also equal to f of x, which gives us the original function. And so, as a result, we could say that the derivative of the integral from a to x of f of t with respect to t is equal to f of x. As an example, let's say we have to differentiate the integral from 1 to x squared of t cubed plus 2 with respect to t. Using the fundamental theorem of calculus part 2, we can find the antiderivative of t cubed plus 2, which will equal t to the fourth power over 4 plus 2t. We will integrate this from 1 to x squared by plugging in the upper bound first into the antiderivative function, then subtracting the antiderivative of f of 1. When we simplify this, we get the derivative of x to the eighth power over 4 plus 2x squared minus 9 over 4. Differentiating this will give us 2x to the seventh power plus 4x, which will be our final answer. And that was differentiating integrals and the fundamental theorem of calculus. Hope you found this useful and have a good day.